So now we'll look at a little bit about this Bohr model. We talked a little bit about the Bohr model, but it's more into the quantum mechanics of these electrons and how they're behaving, going to these different energy levels. And so Bohr is kind of helping us understand that. And you know, when I was drawing this little model earlier, where I'm drawing the energy levels around the nucleus of an atom, we kind of call that a Bohr atom model. So that's where that's coming into play. Okay, so Bohr's work convinced scientists to abandon classical physics, which they didn't want to, but you know, he helped them see a better quantum with the quantum mechanics, that they're not getting rid of the ideas and things, they're just altering those ideas. Einstein had a hard time with it at first, but then, you know, that's what happens always. Einstein was the one that came in and was like, here's the mic drop on this stuff. And he changed all this, everything. And the scientists before him were like, no, this can't be true. None of this is right. And then Bohr comes in and is like, mic drop again. And Einstein is like, no, this can't be true. And so that's how they always are, right? They get set in their ways. But we just build upon those concepts and ideas that they're giving us. And now we're into these quantum mechanics of the atom. Okay, so like it was before the Bohr, the atom consisted of tiny dense nuclei surrounded by lighter and even tinier electrons continually moving about the nucleus. Good. This classical mechanism description of the atom is incomplete, since an electron moving in an elliptical orbital would be accelerating. Okay, so according to classical electromagnetism, the electron should continuously emit electromagnetic radiation. And so these are some of the concepts and idea that he's building up to. Okay, not that the classicals were ideas didn't help us understand these things better, but now we're just adding to those concepts and ideas. Okay. All right. So kind of like talking about, like I was telling you about the types of orbitals. We have an s orbital, we have a p orbital. The way that these electrons orbit will be different than just one particular way. Okay. So Bohr is also incorporating Planck's ideas of quantization and Einstein's findings of light consisting of the photons and energy and those sorts of things and their frequencies. So he's building on those. Here's our energy equation, but the change in the energy is what he's focusing on, because to understand the position of an electron, what he would do is shoot energy at these electrons, excite them, and they would get excited and move up in energy levels, but then when they relaxed, they would emit energy, and he could measure that energy that they emitted so that he could identify the positions of these electrons and things of that nature. So that the change in energy, which isn't something we're really going to focus on or do, but the change in energy there was kind of the idea of how he could do that. Okay? And also was able to identify these energy levels. Once again, those rings are the energy levels. The term for that is n equals 1, n equals 2, etc., all the way up to n equals 7. And the n equals 7 is the highest energy level that any element can achieve. And if we got past number 118 on the periodic table to number 119, we would add a whole nother energy level. It'd have to be a whole nother energy level for 119 to exist. Right under francium is where it would exist. Number 119, if they ever synthesize that. That's what these last ones are anyways. 113 through 118, just a couple of years ago, didn't even exist on the periodic table. Why are they there now? Because they synthesized them. They don't exist naturally. A lot of these elements don't exist in a natural form because they're so radioactive, they just fall apart the second you make them, essentially. So anyways, but the reason we have those last elements now is because they were able to synthesize them. So potentially, could they get to 119? We'll see, right? Maybe one day we'll have 119, 120. That's a whole new energy level. Now we're at the 8th energy level on the periodic table. Yeah?
Is that like for chemists, kind of like their sport, like they're kind of all excited, like, hey, who's going to do it this year? Who's going to make 119?
Yeah, I think so. I mean, certain chemists, yeah, for sure. A lot of chemists, no, they don't care because they're focused on other research.
Yeah.
But there are specific chemists out there who would be very interested. That's like, you're right. That's what they do. That's what they think about and focus on and do. Okay, so those are the energy levels. Once again, here this K is representing a constant. This is Rydberg's equation. We're not going to use it. Okay, showing that constant times the speed of light there, giving you is how you would derive that. So here is showing you different energy levels. So as you move up in energy, you're moving up in these energy levels from one energy. Remember, Planck was talking about quantization of energy, moving from one energy level up into the next energy levels, right? And that's what's happening there. That's what they're showing. Okay, and we're going to talk about some of these quantum numbers that are associated with these energy levels and things. Now, ground state, the term ground state just means that you're an electron in your lowest possible energy, okay? Now, when we talk about this first energy level, we have electrons in that. Those 2 electrons are at their lowest energy. But what if you have 3 electrons? Well, if you have 3 electrons, this electron cannot be in its ground state in this first energy level because that energy level is already full. So its ground state will be here in the second energy level. Okay, so when we talk about ground state, you're in your lowest possible energy state. Okay, whereas if I shoot a photon of light at this electron, I could move it up into other energy levels. Okay, or if I hit this electron, I could move it up into energy levels. And then it would relax naturally back down to its ground state because that's where it wants to be. You just got it all excited, okay? And then it relaxes back down and it releases the extra energy that it had. That change in energy will be released, and that's how Bohr was able to identify the positions of these electrons and things, okay, within his Bohr models. So you can see that happening here where electrons are moving up and down, they're getting excited and things, they're moving up and moving back down into their lowest energy states. And that's what he was doing. Okay. Don't worry about that. I already know about that. Okay. This is just one of those change in energies. I'm not going to give you a question of that nature. Okay. All right. Now, let's talk about quantum numbers. Okay. Like n equals 1, we're going to say that that's a quantum number, or we're going to use specific numbers that identify the sub-energy levels. We have sub-energy levels like S, P, D, and F. And remember that there are different types of orbitals that are associated with these sub-energies. So an S orbits the nucleus as a sphere. The P has the dumbbell-shaped orbitals. And then D just gets into just, you'll see, just big crazy craziness with the orbitals. And then F is just ridiculous. Okay, but the S and P are more the ones that we focus on because we can kind of look at those and describe them more easily than the others. Okay. Once again, just some history. You guys can read on your own there. Okay.